So in our previous video we looked at an experiment that showed that some salts are acidic while some are basic or alkaline, and some are neutral as well. So we might need a new definition for acids. What we used to think of is that an acid is something that neutralizes a base, and conversely a base is something that neutralizes an acid. Acids have a pH of less than 7, well that still exists. Bases have a pH of greater than 7, that's still correct as well. We probably thought that acids have got an H plus ion to give away, so they, HCl, H2SO4, things like that, and that's still true as well. But what we probably also thought is that bases had a hydroxide ion in them, and that's not quite the same as what we're going to ask you to have now. So if you're looking for a good set of definitions of acids and bases, they're on page 214 of Beginning Chemistry. And there's some good ones there. And they are all correct. The only thing that's wrong about them, and therefore not mentioned there, is that they always have a hydroxide. And hopefully last year we sort of pointed out, well, carbonates and hydrogen carbonates were bases that didn't have hydroxides. So we're going to use a thing called the Bronsted-Lowry definition, because it's a much more meaningful one. The Bronsted-Lowry definition is actually quite simple, if you can remember it. Acids are what we call proton or H plus donors. That means that when they react, they will give away an H plus ion to something else. Bases, on the other hand, are what we call H plus acceptors. That means when they react, they'll take H plus off something else. And I've got 3 examples of each to show you how this works, to lead us up to 2 new terms for us this year, Amphoteric and Amphiprotic. You might have met Amphoteric before, but I don't think you've met this one, Amphiprotic, before. And these are quite important for showing the acid and base nature of different substances. Okay, so acids donating hydrogen. The easiest way to show it is to react these things with water. So either dissolve them or react them with water. And we get to see what happens. So the HCl, if it's going to donate an H+, well, we can see it's got an H in its formula. So that's going to disappear, and it's going to become Cl-. Now this thing here, what the acid becomes, is called its conjugate base. Now it actually doesn't have any alkaline properties at all, but after an acid has reacted and lost its hydrogen ion, we call its product the conjugate base. So that's the conjugate base for this acid. The water is actually acting like a base in this case. It's accepting that hydrogen to become H3O+. And it is because of the increase in concentration of H3O+ that HCl has a low pH. If it didn't make hydronium ions, this thing here, then it's not an acid. It is the production of hydronium, or the increase in concentration of hydronium, that makes an acid. So because it has the ability to donate an H+ to the water, then we call it an acid. Now these next two don't, well, the next one is an acid. It's got an equilibrium error because it's what we call a weak acid. It's ethanoic acid, which is at low concentrations, what we call vinegar. It's hard to know which hydrogen to take off this. My hint to you when you meet these sorts of things is don't take a hydrogen bound directly to a carbon. That bond is too strong. It's got to be bound to an oxygen, okay? Or to a nitrogen, because they can also exist. So we're going to remove this hydrogen here to make CH3COO-, the ethanoate ion. The acid has become this, so we call it the conjugate base for that acid. Now this one actually is a base, by the way. This one has got alkaline properties, as we showed in our experiment. It's also going to make H3O+, which tells us why it's an acid. Same thing here, ammonium, we met this in our experiment, is going to lose one of these hydrogens to become ammonia, which we should know is a base. And so therefore is the conjugate base for this acid. And, sorry, I've put 2 pluses there. And it's going to make hydronium ions. Conversely, a base is going to accept a hydrogen. Now you can't show it with one like sodium hydroxide or any of the other very strong hydroxide bases. It just doesn't work. So all you're going to do is show it dissolving to make hydroxide ions. Okay, so this one's actually a really hard one to show. Whoops, where it's turning into these two ions here. So that's a hard one to sort of show. But because it's making hydroxide ions, it's going to make the pH higher. These two here, ammonia and the carbonate ion, are much easier to show. So I'm going to use those ones. And you'll notice the equilibrium arrows. These are what we call weak bases. They're much easier to show it acting as a Bronsted-Lowry base. They're going to accept hydrogen ions. So where are they going to get it from? They're going to get it from the water, because water has the ability both to accept hydrogen and to donate it. It's what we call amphiprotic. So knowing that this base is going to accept a hydrogen, it's going to become NH4+, because it's an H plus ion, not just a hydrogen atom. And if this was the base, then when a base reacts, it always makes what we call its conjugate acid. So this is the conjugate acid for this one being the base. Now compare that over here. When ammonium was the acid, ammonia was its conjugate base. So it's just terminology we need to get our head around. Acids have conjugate bases. Bases have conjugate acids. Now I'm not quite balanced here yet. Just like above, we're going to see an increase in hydroxide ion concentration, which is why we know that this is a base. It's by this going up, the hydronium ion concentration goes down. Last one of these. Carbonate. Now it could take two, by the way, it could become carbonic acid, H2CO3. I'm just going to show its first step because that becomes important for something I'm about to show you next. So it's going to take one H plus from there to make this, which is its conjugate acid. Funny term, because if I check the pH of this, it's actually above 7. It's a base. But in this case, it is the conjugate acid for carbonate. Okay, just a term. It's just a term we need to know. And again, it's going to make the hydroxide ion because that hydrogen has come off here. Now, two other terms that are really important to know. So we've got conjugate acid, conjugate base, we've got acid, we've got base. Two others are amphoteric and amphiprotic. Amphoteric means that it can neutralize both acids and bases. Okay, so it means that it will react with both of them to neutralize them. And the way that you see it is normally you'll see a dissolving effect or something like that. So in this one, we can just balance the equation by having 3 water molecules and aluminium chloride made. In this one here, it actually makes a thing called a complex ion. Okay, so just be aware of the term. You don't have to do the balanced equations for this. Amphiprotics, on the other hand, you do need to be able to do balanced equations for. You need to be able to show amphiprotic things, that's water, hydrogen sulfate, hydrogen carbonate, those sorts of things, where they act as an acid and a base. So if I was to say that it's an acid in the first one and a base in the second one, then I should be able to show that reaction. An acid will donate an H+, so it's going to lose this one here to become CO3 2- and H3O+. And so this is going to be our conjugate base. A base will accept another H+, so it's going to become H2CO3, and because it's come from that, it'll make hydroxides. Therefore, this must be our conjugate acid for that base.